Okay, hi guys. One, two, three, four, five. Now I can hear myself. Okay, sorry for that glitch. I'll be checking the audio uh, to make sure that you can hear me nicely. Okay. So what I was saying was that uh, in the last 2 years here you can see that okay, for section B you're gonna get 3 questions and you're only gonna do 2. Now we know that if we know all the questions to do with nodal analysis, mesh analysis, KVL, and KCL, we're gonna be fine. Okay, we can actually say that most of the questions that actually come here are just KVL and KCL. You don't actually do much of nodal in the very first one. It's going to be more of KVL and KCL, just those ones. Okay, so let's say you get a question to do it with KVL and KCL. Then in here you're going to do your Thevenin and Norton, and you're going to do your capacitor. So there's going to be a capacitor within your network theorems. Okay. So number 2, network theorems, and then we have number 1 being your KVL and KCL, and then number 2 being your network theorems. So if we're able to do, we'll start with these questions obviously, but we know that if we're able to do questions from the fast papers and the tutorials to do with sorry, to do with network theorems, then you should be able to be good at this. Okay, I need to just remove this thing which is that. Okay, let's go through this. This is simple. This is a walk in the park. We should enjoy this exercise. Good job. I managed to remove it. So we have question number. We're going to have question number one, which is going to be KVO and KCL. Then we are going to have question number two, which is going to be question number two, which is going to be your network theorems and capacitance. So we're going to be able to do that. Let's start with what? Network theorems. Should we start with network theorems? Let's start with this question. We should be able to do network theorems. So for you to be able to solve this, it's more like statics. We talked about this in statics when we went through statics. In statics, we saw that they will combine, they would question, and you had to do your chapter 7, then your chapter 9 and 10. Okay? In the same question on beams. And then now here we have the same thing for network theorems. So for our network theorems here, they're going to combine network theorems and ideas of capacitance in the same thing. So the very first part is going to be network theorems. Okay, the very first part is going to be network theorems. Then the second part is going to be you understanding things to do with your capacitance. Okay? Right, so now let's go through it. Let's enjoy. Let me reduce the volume so that it doesn't switch off the microphone. A little bit. Okay, so here we go. Now, what was I saying? I was saying, here's the question. Let's quickly go through it. Using Thevenin or Norton analysis, reduce the figure. So this first thing, I don't have to look at this. For the very first part, I am using Thevenin. I am using Thevenin or Norton. That's the very first thing. And you guys should know that we are always going to be using Thevenin. We're not going to be using Norton. So we're going to be using the Thevenin theorem to do this very first part of the question. Then we're going to do, after we have done the Thevenin, we've done everything, then we're going to now go to the idea of capacitance, which is completely different from this one. So Thevenin, so for you to be able to do this, first thing, you have to be good at Thevenin. And we'll start with this particular question. Then we can even look at other Thevenin questions, and you see if you're good at them. That is how you're going to be preparing for this one. So these are the questions you're going to do. You know, in section B, you're going to do the one with the network theorems, and then you're going to also do the one with KVO and KCL. So make sure you're good at those two. If you're good at those two, you're fine. Ignore inductor. Completely ignore it. We don't have to do it. We don't have anything to do with the inductor. So let's start with this one. If we go through this one, they've given you this big thing. We know that in Thevenin, this is a walk in the park. We should be able to do it real fast. Thevenin is just, you're going to be using the voltage divider. You're going to be using the voltage divider to do Thevenin. And what you'll be doing is, you're just going to be cutting your circuit piece by piece until you get to where you want it. You're going to be cutting your circuit piece by piece until you're going to get to one. You don't look at the whole circuit in one go. You look at it piece by piece until you get to the thing that you want to get to. So if we start here, you're going to cut it here. This is the very first thing you're going to cut. If you draw it, let me have two separate books here. I want to have two separate books, two separate notebooks, so that I can be able to do the question and I can be able to do the answer. So let me do it. Okay, there we go. So from here, I now create my new notebook, and okay. There we go. Let's see. Okay, I've tested. It's writing good. So we are doing the Thevenin theorem. That is what the very first part. If you want to be able to do this first part of the question, it has nothing to do with capacitance. It has everything to do with Thevenin. So you are going to reduce, because what they've said, using the Thevenin analysis, reduce the circuit. So we're just going to reduce the circuit. That's what Thevenin is for. It's voltage divider stuff, so we know that's not even a problem. If you want, you're going to draw your circuit first as it is. So you draw your circuit as it is. You're going to do this. Then it goes like that. If you want to draw the very big circuit, it's just very easy. This is a walk in the park. You can't tell me that Thevenin gives you problems. I'm going to draw it at a smaller scale because I don't have space. So it's going to be like that, then like that. So it's going to then. We'll go to point A. Then you have another point here, which comes down through a resistor. You have another point here, which comes down through a resistor. Then you're going to have it go down into this space. Then you have your capacitor, which we are ignoring at this point because we don't even care about it right now. So anyway, you have your switch. So this is going to be, we can call it our point number 1 and our point number 2. Then it goes like that. So here's the thing. For our Thevenin analysis, we are going to be obviously looking at this side of the circuit, this side here. Yeah, we are looking at this side of the circuit. So what we are going to be focusing on, we're going to remove everything here. We want to simplify this whole circuit and represent it by something very small. So what we're going to do is we're going to start cutting, and we always cut out here. After the first loop, we can say that. And then you can put the values. Put the values of the thing. This is going to be 110 volts plus minus. Here you have 1.5 kilo ohms. Here you're going to have 1 kilo ohm. Here you're going to have 1.7 kilo ohms. Then here you're going to have 500 ohms. Here you're going to have 2 kilo ohms. Then here you're going to have another 2 kilo ohms. Then here you're going to have another 2 kilo ohms. So we have cut there. So what we actually have now, you need to draw what you have after cutting. You're going to have now as the source plus minus like that. It goes to the circuit. Then it makes the complete circuit like this, goes down. Then here it is open like that. And we are going to be getting the potential between these 2 points. We're going to be getting it here. It is going to be the same as the potential here across this resistor. So we are now just going to get it. Thevenin is a joke. So you say this is 110 volts. This is 1.5 kilo ohms. This is 2 kilo ohms. There we got it. So now remember that I told you that Thevenin is voltage divider, TBH. You're just going to be cutting piece by piece, but you'll be just using voltage divider. Come on, you can do it. So we're going to, if I look at this, I'm going to cut here, and I'm going to cut here, and I'm going to cut here. So I can say I'm going to cut like 3 times if I'm saying that. So we can say, okay, since I'm going to do it 3 times, you can call it V Thevenin number 1, then number 2, or whatever you want to do it. So if I'm going to call it V Thevenin the first, this is just going to be, what do I use? We said we use voltage divider because you want to find out how much is going to be going to this 2 kilo ohms. Because voltage is shared in series between these two. So we want to find out how much is going to these 2 kilo ohm. That is going to be the one which is going to be here, which you can call V Thevenin number 1. So this is going to be equal to how much is coming here? Well, you're going to say for potential divider, it is easy. You just say 2 kilo ohm, which is the one way you want, over the total 1.5 plus 2, and both of them are kilo ohm. And you multiply by 110 volts. So you're just going to get an answer. So it's going to be 2 over 3.5. So it's 2 kilo ohm over 3.5 kilo ohms times 110 volts. Then you're going to get your V Thevenin. I punched that. So I'm going to say 2 divided by 3.5. I say times 110. Well, here I'm going to get an answer with a lot of decimal places. Let's just say I decide to put it as 440 over 7 volts. This is going to be the very first one. Then if you want to put it again in as a decimal, that's up to you, as 62.8571. And this is going to be volts. We got it, right? Now, once you do this, you're going to get your resistor, and the resistance is very easy. All you're going to do is you're going to go to any source, and you're going to short circuit it. So you're just going to draw a simple circuit, but it won't be having a source. The Thevenin resist, because when you're doing Thevenin, you need Thevenin voltage, which we saw that you just do potential divider. Then you need the R Thevenin, and to get R Thevenin, you just add the 2 resistors. And how you're going to, when they're in series, how you're going to do it is you're going to make this a short circuit at 110. So all you have is you actually have a circuit where you have 2 resistors now. It's going to be like this. And here you have the other resistor just like this. So this is the circuit which we have where things are actually moving. And this resistor, we know one was 1.5, the other one was 2. So you can say 1.5 kilo ohms and the other one is 2 kilo ohms, which you just say, okay, now for me, it's here's how I'm going to do it for my R Thevenin. This is very important. When you're now doing your R Thevenin for these two resistors, you are going to treat them, like not addition, but you're going to treat them like a parallel combination of resistors. So it's going to be R Thevenin will be 1.5 kilo ohms. You're adding them, but you're adding them in a parallel way. So it's going to be 2 kilo ohms. You divide, you multiply, then you divide by the sum, 1.5 kilo ohms plus 2 kilo ohms, which you're going to put. Let's put 2 times 1.5 over 2 plus 1.5. And you get 6 over 7 ohms. If we leave it like that. So what do we now have? Obviously now we no longer have the big thing. Okay, so now let's remove that first part. We no longer have all this part. Now we are going to replace it, and when we replace it, we're going to replace it by two things, which is the V Thevenin and the R Thevenin, and they'll be in series. So let's do that. So now what we actually have is, let's put the two things. We have found our V Thevenin to be what? 440 over 7. So if I'm going to put it, it's now a circuit, and it's going to be like this. So it's like, all you should now do is imagine if the source is now here, then it goes like this and like that, and but it's going to be in series with one more resistor here. So it's going to be, the resistor is going to be this one, which is the 6 over 7. Then from there it goes to the 1 kilo ohm resistor. Then from there it now comes down to the 2 kilo ohm, and you don't even have to draw the rest of the circuit because we don't need it right now. So then you put it like this, it goes down, and we are now dealing with this part because now we are ending after the 2 kilo ohm, which is here. That is where we are now ending. So if I'm going to put it, we found this to be 6 over 7. We found it to be 6 over 7 ohms. That's a very small value. And here the other one is a 1 kilo ohm, and then the other one is going to be a 2 kilo ohm. So obviously we know we can combine those two that are in that are in series. So if I'm going to say what is going to be 6 divided by 7, I get, then I say divided by 1000. So if I'm going to put it, I have now a situation where it's like this. This is going to be 0 if you are putting this resistor and making it 1, then you have this other one, which is going to be like this. What you know is that the V Thevenin, the second you want, is here. Okay, this is going to be the very second one, the one we want. Okay, which you obviously have to find out. So let's find it. We can find it now. What is it going to be? We can put it. Even if you show that for your V Thevenin, which is the other one which you want, you can show how, even if you put it, you can show how you had another thing which is like this one, 1.7. It doesn't change anything. For you to put this 1.7 in the mix, you could have done that to say, okay, there is going to be a 1.7. Usually that is done. So we could put it like this. But we ignore him. We ignore him in calculations. Where we are interested is here, and we are interested in here. Alright, so your R Thevenin is actually kilo ohms, not ohms, because you are dealing with kilo ohms, so it's actually kilo ohms. What am I thinking? So this is going to be kilo ohms, which when you add together they are in series, so you end up getting 13 over 7 kilo ohms. Then this other one is going to be 2 kilo ohms as well. So this other one is going to be 2 kilo ohms. And what is the volts? It's 440 over 7 volts. So we do know that this is 440 over 7 volts. That's why we are not rounding off, because we're still in the midst of real calculations. Now, to get the V Thevenin the second, it's just voltage divider. We talk about it all the time. So it's going to be 2 over 2 plus 13 over 7. Then we multiply 440 over 7 volts. So this is going to be 2 over, open brackets, we say 2 plus, open, 13 over 7, close. Then you say close again. So this is going to be 2 over 2 plus 10. You get an answer. Then you say times 440. You get an answer. Then you say divided by 7. You get 880 over 27. So this is going to be 880 over 27 volts. And you might as well just put the decimal value, because they could be marking against the marking key for that. 32.5926 volts. Then, now we're going to draw our R Thevenin. It's time to do the R Thevenin. Okay? And to do the R Thevenin, what do? We just take this, but we're going to short circuit the source. So in actual fact, you'll be just having something like this. And you're going to have them in like this. And in here we're going to have 13 over 7 kilo ohms. Then in here we're going to have 2 kilo ohms. So what you're actually going to do is you're going to say, well, R Thevenin the second is equal to 13 over 7 times 2 over 13 over 7 plus 2. And we're going to get an answer. So let's put that in a fraction. Fraction will be open bracket 13, open bracket again, and then you're going to say 13 over divided by 7. So it's going to be 13 over 7. Then we say this is times 2 over, in the denominator is 13 over 7 plus 2. You get a 26 over 27. So it's going to be 26. In here we're getting an answer. It's 26 over 27 kilo ohms. We're doing well so far. So now what we do know is that we are again now going to simplify, because we have used all this up here. All this up. So now what we are actually remaining with is we're just remaining this 1.7 with this 1.7 and this 2 and this 500. Okay, so it's actually going to be like this, then it goes like that, and then it goes like that. And 500, we will now say 0.5 kilo ohms. Then this is 2 kilo ohms. Then we are going to have it like this. There we have it. And this is now going to be V Thevenin the third. And this will help us. So now what we're going to do is let's put the values of the things that we found. We found to be 880 over 7 over 27. So we found it to be and this is volts. Then we have 26 over 27 kilo ohms. Then here we are going to have the other value, which is 1.7 and 2 and 500. So this is going to be 1.7 kilo ohms. Right. Now let's go ahead and let's do that. So I'm going to say to get V Thevenin number 3 is going to be again it is the voltage divider. But first add those two. Let's first add those two. So we're going to have a new circuit plus minus. So let's put that. So here we have it as 2 kilo ohms. Let's add. So I'm going to add now. I'd say fraction 26 over 27. Close the bracket. And I'll now say plus 1.7. I'll get it as 719 over 270. I'm sorry for that. But now, and we know the value of here. It is 880 over 27. So now let's go ahead and let's do the rest. It is going to be, you say V Thevenin the third is going to be 2 over 319 plus 2.0 over 880 over 27. And here we go. So here is going to be, sorry for that, I didn't add nicely. It's 2 over, sorry. It's 2 over 2 plus, is it 719 over 270? Something like that. So because we take this one, we divide by the total. So it's 2 because we want the voltage at 2. And is what value is that? Let me see again. Sorry. 26 over 27 plus 1. Plus 1.7 rather. It's 719 over 270. Okay. So now we can get our answer. We can say 2 over 2 plus 719 over 270. Then times 880 over 27. You get it as 13.9793 volts. There we have. That's the value. So this is going to be V Thevenin the third. And now we can go ahead and get the current. So and to get the R Thevenin, to get R Thevenin, we know what we're just gonna do. We show them as if they're parallel. And here what you get? 719 over 270. Then here what you get? 2 kilo ohm. R Thevenin the third is now going to be 2 times 719 over 270 divided by 2 plus 719 over 270. Then we'll see what we get. $1.1422 kilo ohms. All right. Look at this. How good is this? So now we have found this Thevenin again. We have found the Thevenin again. So now we just give me one sec. Let's do the second, which we now have. Okay. Sorry, I was trying to help somebody. Let me just finish it. Let's draw the second that we now have. We know we have that 500 thing, but everything else is gone. So everything, all this stuff is gone. And we are removing, and we put with what actually remains. So what we actually now have is just going to be something like this. We have the source, which is going to be in C like that, then here again. Okay. Then what we actually have now is what? Then we have one other at the back. So we actually end up having 1.1422 kilo ohm plus 0.5. We have another one which is going to be 0.5 kilo ohms. Then this is going to be it. We just have one more thing to draw. Where's the question? This one, 2 kilo ohms. And this is going to be 13.9793. 13.97 whatever. We can just put it as 14.0 volts. If you want to put it with 13.9793, then let's simplify it. So actually end up having plus minus, these two will add up. This becomes 1.6422 kilo ohms. Going to like this, then it goes like that, and like this, and it comes like this. 2 kilo ohms. Position 1 with the switch somewhere here, position 2, and we now know this is 13.9793 volts. We've done the reducing. Did it have anything to do with you knowing capacitors and stuff? No. Don't mix the questions. These are two different questions. Then here they'll now say, Captain, please determine the mathematical expressions. Now they want you to find the mathematical expressions for the variation of current and voltage in the capacitor following the close at. So they are now saying we have it goes to position 1 and position 2 at this whatever. So they want the formulas, mathematical expression. They want the formulas. For what? For current with respect to time and voltage with respect to time. When you close it at position 1. So what you do, positions tell you whether something is charging or discharging. That's what positions tell you, where the switch is. So here, if it is at position 1, that means it is charging because there is a source. Now, so that means this thing is charging. This capacitor, here is the capacitor. It is charging. And you can see from the question that it was 0.1 microfarad. 0.1 microfarad. So here we have all that. It's at position 1. We know that the capacitor is charging. So now our work is to just put the equations for a capacitor. When it charges, then when it discharges. Here what they want is when it does what? Here they want you to put for when the capacitor is charging. They said in position 1 you should determine the mathematical expressions only at position 1 at t equal to 0. So here at position 1, here we're following the initial things, and we want to find out to say what is going to be the value of that thing. Let's just put, I once did an exercise with you, and it is now you who should remember this. For a capacitor, let's put charging versus discharging. But okay, for here to answer the question, we need when it charges. We know that tau is equal to RC. This is the time expression. Then what we know is that voltage at some power t is going to be equal to the maximum voltage multiplying 1 minus e to the negative t over tau. And then you can now say current at some point in time t. This is for charging. The voltage at some point is max then 1 minus. Then this is going to be what? V over R. Then this is going to be e to the negative t over. Here we have it. And it is actually, we can just write it like this to say I at some function time is big I, then e to the negative t over tau. Here we are going to be finding what they want. Variations of current and voltage in the capacitor. Okay, there we have it. If it was discharging, this V in here is 1 minus, right? For discharging, now what you just do is you're going to say this is going to be V of t is going to be equal to V e to the negative t over tau. Then IT is going to be the very same thing but with just a negative sign. Negative I, then you have e to the negative t over tau. So here we have it. We have our IT. Which if you want to find this big I, which is going to be the maximum current, it's V over R, but there's a negative now, e to the negative t over tau. There we have it. We don't want this section for this question. We only want charging. You have to remember this stuff. Now, what do? We go to number C. So now where they said when the switch is closed on position 2 at this time, determine the new expression. Determine the new expression for the capacitor current and voltage. So to do number 6, it is now the time will be 100 milliseconds. So let's quickly put it. I need to put it like this. Now, what are we going to get? We start by getting what? Yeah, okay, we know that our time is going to be 100 milliseconds. You could even change that. Now here they say determine the capacitor current, and then they want the capacitor voltage. So anyway, here we have it. This is where we are. And we want to find out to say what is going to be the value for, sorry for the glitch in network. It's so bad. I hope it's not going to disturb us. So all you have to do is now find an expression. Because this switch is now closed, they want a new expression for the capacitor current and voltage. What is happening at position 2? At position 2, we know that this thing is discharging. So we are just putting these very same equations. So it's going to be v at some function of time t is going to be ve to the negative t over tau. You should practice, which is going to be v at some function in time t is equal to. Here you have been told that you are at t equal to 100. Okay. (100 milliseconds), that's times 10 to the negative 3. And if you want to actually put tau in here, your tau is just RC. I should have actually gotten it for this previous question, this part 1, because I have the R. It is this R which is in series with my resistor. That is for part 1. This is 1 point whatever. And I multiply by C the capacitance. And I'm going to get the time constant, the tau. So it shouldn't be that hard. So that is where the other marks are. Let's go back and let's fill in the thing. So let's say tau is equal to RC, which is just going to be, what is the R? Always take the R and the C. One, two, one, 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 1, 2. Okay, looks like my sound is back. Good. Sorry for that. I'm also following it through to try and make sure that anytime the sound is gone, I fix. So sorry for that glitch. Sorry for that glitch. Let me fix it. I've tied it down so that it doesn't do anything. Right. Now, we were just saying, all we have to do is to finish it up. This part we are now doing is capacitance. Here, what we are now doing is just capacitance. We are trying to make sure we are now getting the maximum marks. We are done with the network theorems part, because we know what network theorems was. Network theorems, we are done with it, man. Now what we are doing is capacitance. So it's now about you understanding to say, okay, what is happening at position number 1? Then, okay, when we move to position number 2, then what happens? So when I have my RC or my C and my R, I can get my tau. And when I'm getting my tau, that's very important for me to get my tau. I can start to feed it into the expressions. Okay, I can start to feed it into the expressions. So don't panic. This is not even hard. Okay? They can give it to you at anything. They can give to you an expression and they say, please find when this is like this. Please find when this is like this. Whatever situation. So you must get tau. And when you get tau, you can now start to do your calculations. So in here, I would be saying, okay, when you're given a specific point in time, here when we're saying, whatever the time we're dealing with is a time from the time 0 going on, because you close it at position t equal to 0, right? So in here, that means we are dealing with time greater than or equal to 0. So in other words, your tau was t minus 0. That's what we'll be having from time bigger than 0 over t minus 0 over tau. So now you'll be having your tau. What was our tau? Let me put it in the calculation. 1.642 exponent 3. Then we say times 0.1 exponent negative 6. Here we got it as 0.0001642. Okay? And if we say 1 divided by that, if you wanted, you'd be having it as here. Okay, so we are now dealing with the time. We can now just start to put, we can now just start to put. So from here, we can now put anything which we need. And we're just, these are just expressions. So you're just writing now to say, since I have you, it's just going to say V as a function of time is going to be V multiplying 1 minus E over negative T over 0.0001642. You can put those things and leave it like that. So that'll be now your 3 over your whatever. And remember that here you also have V over R. This for your IT, okay? This V is going to be the maximum voltage, which if we're going to say it's going to be my maximum voltage for here, if I'm dealing with this, I'm looking at the voltage that I'm going to have across the capacitor. Here that means when it's at position number 1, how much is going to come here? Okay, that is what I'm doing. The voltage across the capacitor. It's going to be what? When I only have my capacitor now. I've done the Thevenin, I've reduced it, and now I want to find out how much voltage will be across my capacitor. Oh, we know when I am putting that voltage, okay, when you're now just going to be putting the voltage across the capacitor, after it has done all the charging, now you want to put what voltage is going to be across the capacitor. You have to swap because it has been charging. In here it is at position number 1, so it is going to be charging. And its maximum after all that charging, what is that going to be? So let me continue with B. This is going to be V as a function of time is going to be equal to, start with this. This is going to be what? We go back and we take this, but we change the sign. Okay, because we are now dealing with how much voltage is going to go to your capacitor. That is the thing where we have it. So where we first found our time constant. Remember, we first found the time constant. If you look at many situations, you find situations like this, which we have done. After finding the time constant, we found it. Then we expressed our V as a function of time. So we said, if I'm putting it after finding your time constant, here's where you found the time constant. Then you express V as a function of time. You can first do V as a function of time and then you start expressing from there. Because now the next thing is going to be how much goes to the capacitor is the very same thing as the supply. Because it's just in series with your thing. So it's going to be the very same thing as the supply. What is going to be this supply? 13.9793 blah 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 blah. Okay? Which is just the same as, almost just the same as saying 14. So you're going to put it to say it's going to be 13.9793 kilo, no, it's just volts. Then multiplying 1 minus E to the, we now say it is T minus 0, okay? E to the, you're putting it, 1 minus E to the, now you're putting the things. T minus 0 over your tau, which we found your answer. To 0.000, put it as it is, 0.0001642. Then you would have put your thing. To the negative T minus 0, by the way, for this one. then you can have it like this. Now, since you want, here you have it, and this is going to be for, we can say time greater than 0 and whatever. Here you go to determine the expression for the capacitor current and voltage. We also want for current. So if we want for current, we are now doing for current. First, for this top one, we are doing for current, okay? And we know how to get the maximum current. This Imax, it's already given to you as V over R. Okay, and you can get your maximum current. This is for when you're now trying to find the maximum current. Here we can now have it. Okay, you can put, here we have found for V, so you leave it like that. That is going to be the one for V. We're now going to say I as a function of T. Now what we need to do is going to say what? V is IR. So here we do know the resistance. What is it? It's like you're going to say this is equal to 13.9793 divided by the R. What do you find as R? 1.6422. So divided by 1.6422. So if you're putting this, since it's 1.6422 kilo, so it will be 1.6422. It's times 10 to the power 3, obviously, because it's kilonewtons. Then we multiply e to the negative t over tau, which in this case, again, it's just t minus 0 over the tau, like that. And we do know what our tau is. You have your 0.000164. Then we are now going to do our expressions for C, for part C. The very first thing we did was to recognize that it was now discharging. So we use the equations for discharging. I'll make you cram them one more time. I'll take you through them as well, just to make sure everybody is good at the equations for charging a capacitor and equations for discharging one. So anyway, this is still going to be V as a function of time, is going to be the big V it had there. Here they say that it is going to switch at t equal to 100. So we need to find out what was the V at t equal to 100. Then we are going to use it here as the max. So here, at 100 milliseconds, that means you're going to have at sorry for the problems I'm getting. Okay, so what we do know is that the big maximum was going to be, we actually had it. What was it? 13.9793. So it's 13.9793. And here it is e to the, because what we now want to find out is, we want to find out to say, at 100 milliseconds, was it, because it switched at 100, was it full and charging? So you're going to get the charging one, 13 point V, then it is 1, then we have it e to the so it'll be here. Sorry, you say 1 minus e to the negative t over tau, which is going to be 0.000164. So now our time v of 100 milliseconds is going to be 0.1. To the negative 0.1, so v of 0.1, it is going to be 13.9793 multiplying 1 minus e to the negative 0.1 over 0.000164. Now we put this in the calculator. 13.9793 open bracket 1 minus alpha e, so it's going to be e to the power of 0.1 over I'll actually get the same answer, 13.9793. So that means this thing had reached full charging. We first check back in the full charging, and this, the point where you switch, if it is full, that point where you switch is going to be the maximum voltage. Okay, are you hearing me? I don't know why I can't hear myself. I can, yeah, 13.9793. All right, so now this is going to be the answer. Remember, when you're now doing this one, when you move the switch, first check what is going to be the maximum voltage. Don't just assume that's maximum, because now you're going to say V. We now say V as a function of time is going to be V multiplying. Now we are in discharging. Don't forget, now we are in discharging. So for V, there's no 1 minus in discharging. It's V e to the negative t over tau. Now it is going to be 13.9793. Then it is going to be e to the negative. Now we are putting the values. We want V as a function of time. So it's going to be, now we are putting, okay? Here it is from 100 going up. Okay? Do not forget. We are now at 100 going up. So we have found the first, we have found it. Now we can even put an expression. So we found the value, but here we can now even put an expression. Over tau, which is 0.000164. There we have it. So now we can say I as a function of time here. Let's put it. For our IT for discharging is negative V over R, then e to the negative t over. Which now we have our V, 13.9793 793. Over the R, you can go get that R. It was there a while ago. We got the same value. I'm sure we got it here when we did the division. Here it's 1.6422 times 10 to the 3. Yes, 1.6422 times 10 to the 3 ohms. And this is going to be e to the negative t over 0.000164. Which, whatever answer you're going to get here, and you have e to the negative t over whatever over 0.000164. So either way, you can find this for I as a function of time. Once you have it, then you have done the expressions. And you should get the 5 marks. So anyway, you are going to get a solution, and you'll be having I as a function of time, and you can have all that. So this is how you're going to do your so yes, you can get a solution, and you'll be having for VT, then you can have IT. Here's going to be a solution. So yeah, this is very, 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 very easy. That'll be a final solution. So if you can put it that way, then wow, that's good. And yep, that's going to be it for this, eh? Now, anyway, from if we plot the current waveforms for D, we should show your capacitor charging. There's going to be a capacitor charging. Then it's going to be switched and it is going to discharge. So there we have it, and we know that here so yes, here we get that max. We know that at 100 milliseconds, that is when it's going to start discharging. And from 100 going all the way to 200, that is what you'll be having. This is at 0. You can put, so sometimes you can put it going down like this, then show it then going back up like this. Anyway, we have put some of the things. You can improve on my diagrams to make it look better. But yes, somewhat of something like this is your solution. But I wanted you to see the Thevenin and to see the network. Okay, that's network there. Then to see things to do with capacitors. It's not the same thing. It's two different things. By the way, there's something which we need to adjust. Is the R for discharge. Let me go to it. All right, so yes, here's some of the thing. I don't know what is going on. I'm going to have to balance my audio and stuff. But here you have your t and over the tau, so it is whatever e to the negative t over tau. But if you look at some of the work which has been done, you may see that you need to have specifically been told that at this position there's going to be a change. So what we do know is this thing went to the other position. It went to position 2. So the second which it is now on to get tau, remember it is RC, which is going to be the R is now 2 kilo ohms, and then the C is 0.1 microfarads. And you are multiplying. And it's 0.1 times 10 to the negative 6. For the R, let's do 2 kilo ohms. So it's 2 times 10 to the 3 ohms plus 0.1 times 10 to the negative 6. And then we find out what is the tau for this. Once you can get it, then we're going to put it here and here and there. So it changes everything. You can come and put that tau, that new tau here. You come and put the new tau, and in here we know that it is, you add, it is actually the R which we are dealing with now is an addition. It's now going to be the R here, 2 kilo ohms. So there we go. We have it, and it is, if you say 13.9793 over 2 times 10 to the negative. Then we can have the solution, okay? So yeah, we will go through the questions in the solutions and try in the tutorials and try to compare as well. But this is the idea, and I hope hopefully this one is gonna come and you'll be able to do it for tau and over RC. And sorry for the back and forth. Get an answer here, and then we are going to come and put it here and then we'll get one here. So now what we need, you have seen how to do these ones that ask, and it's always they come. There are a lot of marks for your V-Thevenin and everything. It's just a bit of a joke. Now I would love to do those for Nodal, but I know that for Nodal you have the solutions. But if you can just see all the solutions for nodal analysis, and if you can just see all the solutions for this capacitance type stuff, I did another one in the site where I posted the video. If we can do all the questions on capacitance and the theorems, it's obviously Norton's theorem, so we'll talk about it. If we're able to do that, then we should be fine. And then we have the KVO and KCO. So if we've done those questions, then it should be good. Let me give you a few minutes, 5 minutes or 1 minute. Sorry, 2 minutes. 2 minutes. Then I'm going to look at the next thing. I need to drink water myself. Okay. Let me confirm if you can hear me. All the time, I have to be confirming. Can you hear me now? Remember, don't forget the structure because the structure will protect you, right? So what we do know is that we there's one way we're going to be using Thevenin, and after doing Thevenin, we're going to use the ideas of capacitance. Then there's going to be one where we are going to be using the KVO KCO type thing. Let me see in the 2023 paper the question to do with Thevenin as well. Section B. Try to increase the volume if my volume is, I don't know if my volume is that low and how low it is. So if so it's the very same question. So we know that this whole part, this one here, we learn it under Thevenin. This one has nothing to do with capacitance, but we learn it under Thevenin. Then we are going to remove all that and represent it using one thing. And then this is the stuff. Once we have it, we can start to apply things for capacitors. Okay, for capacitance. And there's some things I'll remind you towards the end to make sure you can see it. And yep, that's going to be how it does. Now, yeah, they said when the okay, this is going to be what it is. We know there's going to be a question on KVO and KCO. This question should be there if you look in your tutorials. You should be able to find these questions here. The tutorials to do the tutorials to do with KVO and KCO. Can somebody send me that tutorial, please? Just so I confirm what I'm saying before we solve it together. But I'm pretty confident that it should be there. Like if we do for KVO and KCO, let me try to find the tutorial. I think I have it. This one. Okay, good. Let's talk about it real quick, okay? Let's talk about this tutorial. I'm sure one of these questions should come. You know that one of them is coming as your number, is as in the section B, as the first one. Then you're going to have then you're going to have the one to do with the network theorems, which you have been doing, combined with capacitance, and then you have 4 inductors. KVL and KCL. And we should be able to talk about it real quick without wasting any time. So let's start with the very first one. There's something which I'll need to teach you here, which is going to be very important for you when you're solving these things. So let's talk about it. Here they are going to say, find the number of these type of questions. You should solve them quick, fast. Find the number of essential nodes, number of essential branches and meshes. How many unknown currents? How many? Which mesh? Deduce all equations. If we ignore this one for matrix form, okay, we'll talk about it. But if you do 8, the first one, 8F, should be quick. You should do it in no time. So let's talk about it. First of all, they're saying find the number of essential nodes. Well, if they're saying the number of nodes, we know that nodes is just where you have. So here, this is node number 1, where you have 3 or more things meeting, 3 or more cables. Here, this becomes our number 2. Then here it becomes our number 3. So we have how many nodes? We are going to have 3 nodes. Then it's going to say, please find the number of branches. Now, what we do know is the number of branches, okay, if we put, oh, by the way, we have here, I can have this, there should be the ground node, so I should always include it. I almost skipped it. There's going to be this one at the ground where they all meet. You just put it up, so I can say the nodes are actually going to be 4 nodes. And then now they say the number of branches. Number of branches is just path that goes from node to node. So I can say here in yellow, there's going to be number 1. Then we are going to have number 2 in green. Then we have branch number 3 in red. So number 2, branch number 2. Branch is just from node to node. So there we go. Now we can have this one again, which goes to this. This becomes number 4 in purple. Then we put 1 in blue, becomes number 5. That's branch. That's branch number 5. Then we are going to have here in orange as number 6. Then we can have 1 here as number 7. I need a different crayon color here. Here we have the 7 branches. So we are going to have how many? 7 branches. Then for mesh, we're just going to have, it's like these loops which are like this. So we can call it number 1, mesh number 2, mesh number 3, mesh number 4. So we're going to have 4 meshes. Then here now they're going to say how many unknown currents. So if you want to find the number of unknown currents, it's going to be the number of branches, 7 minus 1, which is going to be 6. So you have 6. It's always 1 less than. It's always 1 less than the number of branches. How many independent KCL equations can you find? How many independent KCL equations are you going to find? Well, if I'm doing independent KCL equations, the number of KCL equations, if I want to put, remember for unknown currents, it's just going to be the number of currents in each of these branches. You're going to have the number of unknown, but what we do know is that this branch at the bottom where they are going to come and meet, we can say from this node where they meet and whatever, they'll be joining each other again, so it's like it'll be back to the same. So let's go and see. Number of KCL is going to be the number of nodes minus 1, so it's going to be 4 minus 1, which is going to be 3 KCL equations. Come on! How many KVL equations can you find? If you want to find the number of KVL equations, it's just going to depend on how many currents that you have that you don't know. And how many currents do I have that I don't know? I have the number of unknown currents, 6. So how many KVL? KVL depends on the number of unknown currents, which is just going to be 6. The number of KCL is going to depend on 1 minus, this is number of nodes. Come on, because we know that the KCL equations are from nodes. So it's the number of nodes minus 1. Then KVL is going to be the same as the number of what? Is going to be the same as the number of branches. The number of unknown currents, rather. 1 minus the number of branches, if you want. Now we can actually have your number of unknown currents being the same as the number of branches. Remember, because in each branch there's a current. But in here they are combining to meet at the center, so we are going to do that. That is why I'm doing it. Either way, let's talk about what else are we now going to put? What else are we now going to put? Which other question did they ask? Which mesh should be avoided? We are now doing E. We're just doing the questions that they ask us. Here they are now saying which mesh should be avoided when applying KVL. You always avoid the mesh with the current source. So mesh 1. Why? Because it has a current source. It's very hard to know the voltage of that. So we always ignore any mesh with a current source. We always ignore it. Okay? So now deduce the equations which help to find the current. This question for deduce is loved in the exam. Don't ignore these questions. Let's quickly do it. In this branch, we're going to put current code current number 1. Then it splits into these 3, right? And in this 3, we're going to have the branch current. So in here, we say there's going to be current number 2, number 3, current number 4. They all come, and what happens? 1 will go there, 1 go there. This becomes current number 5, then this becomes current number 6. Then we're just going to have this other branch where they come and they meet, and this is going to be current number 7. And when they come and meet again here, they become all the way current number 1 again. But this one is not part. It will come and join. If we can put it, we'd put it like this to say it is actually going to come and join here. And there's going to be your I4. And in here, there's going to be I1. So you understand it better. So anyway, how many unknown currents did we have? We say it's 6. We should also say 7. Number of branches, the same as the number of branches. So the number of unknown currents for me. But either way, you can still say 1 minus the number of branches and say 6 unknown currents, because we can say this current in the first branch we know because we are told that it is 8 amps for us. Here they say 8 amps, so simply because of that, we'd say 1 minus the number of branches. If it was not because of that, the number of unknown currents was going to be 7. We would say 7 for if we don't know the current in this first branch. Okay. Anyway, we did have a current source, so we knew the current in this first branch. And the current in this first branch was 8 amps. There we have it. Deduce the equations which permit us to find the currents in the circuit. We start to do it. Here is going to be at every node we are going to apply the KCL, and it will give us 3, because it will give us nice 3 equations. So let's say we can say at node A, what do we have at node A? Which currents are coming in? It's I1. Then you subtract all the currents that are going out, minus I2, minus I3, minus I4. This should give us 0. That's going to be at node A. Then we go to the next node, which is going to be node number 2. And then we have node number 3. We are not going to use the ground node because the ground node is the very same as the others. So we're going to do node number 2. I2 is going in, and the ones coming out are I5 and I6. So you can say at node B, you are going to have I2 being equal to, you're going to have I2, we can say I2 minus I5 minus I6 is equal 0. There we have it. Then we can have now to say node C. For node number C at node 3, what do we have? I5 coming in, and we also have I3 coming in, and then I7 coming out. So you're going to say I3 plus I5 minus I7 is equal to 0. There you have the first 3. Now you need to make the last 3. 3 more from your meshes. Right. Let's go ahead and let's do our mesh. Let's go ahead. Are we going to do mesh number 1? No. It has a current source. So we're going to say mesh 2, mesh 3, and mesh 4. Let's go for it. Let's go for mesh number 2. What we just know is this simple. If you're going to be, look at the direction you are moving in your mesh. If the direction you're moving in your mesh is going to be the same as the branch current, then that resistor will be negative. Remember, you are expressing everything as IR as voltages, okay? So if you want, you're going to say, let's start. So I'm going to go like this. Let's see how I meet R5. What is the branch current? I4. Where is it facing down? Which way am I going? I'm going up. So are the directions the same? No. So it's going to be positive, okay? So in here, there's going to be positive. The V at R5 is going to be positive. Then we go to the V at R3. Which way is it going? The branch current is I2, is going this way. And which way am I going? I'm also going this way. So it's the very same direction. So is it the same? Yes. So that means it's going to be negative. So minus VR3. Then we are going to have here at R6 as well. And what happens at R6? Which direction is the branch current going? It's facing down. Which direction am I going? I'm going down like this, clockwise. So what is it going to be? It's going to be negative. So minus VR6. This is going to be equal to 0. You are putting like that. You see? So VR5, what is it going to be now? What is going to be my VR5? My VR5 will be, what's the resistance? Remember, it is resistance times the current. So it's going to be resistance R5 by the current I4. So R5 I4. Then minus V at R3 is going to be, what's the branch current? I2 times the resistance is called R3 minus at R6, what is the branch current? It's I6. What's the resistor? Also R6. And this is going to be equal to 0. We'll call this our equation number 4. This is going to be equation number 4. We want 6 of them. Then we are now going to say mesh number 3. Mesh number 3 is simple again. We're going this way clockwise. So it's like we're going like this, like this, like this. That's the way we're going. But we like to put it round like that. Give me a second. There's an urgent message. Give me 1 second to respond. 1 second. Okay, let's finish this up. We don't play with this, eh? You can now say 5. Wait, am I done? No, I'm at mesh number 3. Mesh number 3. Just compare the branch current. In here, the branch current is facing down. It's called current number 4, right? No, it's called current number 6. Current number 6. Then we have current number 5. Then we have current number 7 with an R7. So you're just going to say, okay, if I go like this, we are meeting branch current number 6, which is facing down, but we are going up, so it's going to be positive. If the directions are different, it's going to be positive. So V6. Then we are going to say, what about this at R4? We can see that the branch current is facing there. We are also meeting the resistor, which is here. Oh, so if it's the same, then it's going to be negative. So minus VR4. Here we have VR6. Then we say minus VR4. Then we have another V, which is where? At R7. So it's going to be, where is the branch current facing? The branch current, branch at 7, it's facing down. And what about the direction we're going? We are also going clockwise, which is going to pass down. So it's going to be the same. So it's going to be minus VR7. This is equal to 0. VR6, what is it? It is I6R6. So it's going to be R6 by I6 minus VR4. What are you? The branch current is I5. What about the resistor R4? So it's going to be R4I5. As R4I5. Then minus VR7, the voltage across R7. What is it going to be? It's going to be negative. And since the current is going down, and this is going to be minus R7I7 is equal to 0. This is going to be for mesh number 3. Then we are now going to do for mesh 4. For our mesh number 4, what do we have here? So we have for mesh number 4. Let's see for mesh number 4. We go for it. Okay, we know that the mesh is resolved this way. So let's do for mesh 4. For mesh 4, what do we have? We can start with this. We have R1, so we have VR1. We have R2, so we have VR2. If you want, you can first put them. So it's going to be, if you want to first put them, it's going to be, you have VR2 plus VR whatever. You know what I mean? We can VR1 plus VR2 plus VR4 plus VR3. So VR1 plus VR2 plus VR4 plus VR3. It's actually, when you put the V's, you are supposed to put them as adding, but when you start to put their things, you can now look at the signs when you are now replacing. So I'm going to say, what is my VR1? R1 is going to be I3 multiplying R1. And you can see, where's the direction for I3? Is the same as the mesh. The mesh is going this way. It is also going that way, up then right. So it's going to be negative. So it's going to be negative R1 I1. Is it I1? It's I3. So sorry, it's negative R1 I3. Then you have VR2. What is it going to be? That's again negative I3 R2. So it's going to be minus R2 I3. Then we have VR4 is going to be, now we are going clockwise, so that means we are coming like this. And it is opposite the direction in here. This is a branch current code I5, which is meeting R4. So it's going to be positive. So plus R4 I5. Then we are now going to say we meet again I3, where I2, it is I2 facing there in this branch. We are coming this way. It is going that way. So it's going to be positive because it's different. So it's going to be plus R3 I2. So it's plus R3 I2. This is going to be equal to 0. And there we have it. This is going to be our equation number 6. So we now have 6 equations. And we are done. We have done all the way up to saying deduce. And I don't want you to do it this one where it says put into matrix form. You're not going to do that. Never, ever, ever, ever. Now we'll see some questions. Here it says conclusion about the use of Kirchhoff's laws. They're saying conclusion about the use when you're not gonna do the idea of putting them into matrices. Matrices. Okay, never, ever, ever, ever. Okay, so yeah, what can you say about the conclusion? You can talk about how this is going to be a very long calculation. So say the use of Kirchhoff's laws will lead to a long calculation because there are many equations. Okay? So you're now writing that to say use of Kirchhoff's laws will lead to long computations as there are many equations. As there are many equations. That is what you say. So now we are going to have question number 2, and we see how it goes, and number 3 and number 4. If we know these things, then we must be able to solve question B. One of the questions is going to be one of these questions. You are guaranteed. You are guaranteed. Don't worry about that part. You are guaranteed that you are going to have what? One of these questions as one of the questions in your section B. So let's go ahead and let's do the second one here. Let's see how it goes. Kirchhoff's laws, blah, 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 for the following, find the number of essential nodes, whatever. We know that all the way up to E or F, deducing, this is going to be a walk in the park. This is going to be a walk in the park. We should do it in minutes. Within the space of a few minutes, or 1 minute, or 2 minutes, or 3 minutes, or whatever, you have gotten all these marks. You do not ever lose these marks. So let's do that part. What am I going to do? Here is going to be my circuit. So obviously, the current that comes from the source is going to be current number 1. There's no need to think about that one. The current that comes, there's some tricks that I need to teach you as well for this type of question, okay? So we know that the current that comes through from the source is going to be current number 1. We have a node here because we have 3 or more wires. We have another node here. 3 or more, we have another node here. 3 or more, we have another node here. So we're going to have, if we call this A, there's going to be B, there's going to be C, there's going to be D. So how many nodes do we have? We are going to have 4 nodes. Either way, when it separates here, you're going to have current number 2 and current number 3. Then it goes like this, and here it's going to meet, and this is going to be current number 4, and this is going to be current number 5. And then here, this is going to be current number 6. So what you are doing here is not for solving. Just giving them as current number 1. Because remember, come on class, come on. Let me remove and so that we agree together. We said, let's put the nodes. If I put the nodes, I have node A, I have node B, I have node C, and I have node D. And if I have node, then I'm going to count the number of branches. Here I'm going to have the first branch. Branch is always from node to node, the wire. So here I'm going to have my branch number 1. So there's going to be a current in there, in that branch. Then if I come here in this second branch, there's going to be a current, there's going to be some current too there. In each branch, there has to be a current in each branch. Don't forget that. Each branch should have its own current. So in the green branch, I can call it I1. Then because it meets the node A and splits, here I can call it I2 in the yellow branch, the branch number 2. Then I'm going to have branch number 3 in blue. I'm going to put a current in that branch. That's going to be I3. Then I need to put a current for another branch, which is going to be this branch, and I'm going to call it I4. And you make it face wherever you want. If you want to come like this, then you're going to have a current which comes out of this branch, which is going to be, we need to choose a color like this. This is going to be current number 5. So this is going to be I5. Then here we're going to have orange, and this is going to be the 6. So we are going to have I6. And this idea of saying I1 all the way up to I6 is not for solving. It's for the rest of these questions that they want you to do in your exam. You need to do this. Now let's do our meshes. We're going to have this as mesh number 1. This as mesh number 2. Here as mesh number 3. 3 nice meshes. Okay, let's start the questions. Find the number of essential nodes. 4. We're going to have 4 essential nodes. Essential branches. How many did we count? 1, 2, 3, 4, 5, 6. We counted, eh? The number of branches is going to be 6 branches. So the branches is going to be 6 branches. The number of meshes, we saw that it was 3 meshes. Then how many unknown currents are there? In this case, you're going to have 6 unknown currents, because our source is not a current source now. Our source is now a voltage source. So we now have, in every single branch of yours, you don't know that current. So it's going to be 6. Then how many independent the moment you say KCL, this one does not change. Nice for it. Is the number of nodes minus 1, which is going to be 3. So it's going to be 3 independent KCL equations. How many KVL equations can be found? If we're going to say KVL, then what are we going to say? We would say to you, how many unknown currents did we have? Total 6. So we have 6 currents to find. How many equations do we have so far? The KCL 3. So how many more do we need here? 3. So we're going to need 3 KVL equations, because the equations should be the same as the number of unknown currents, so you can be able to find them. Which mesh should be avoided? The one with the current source. Do we have one with a current source in number 2? This is a voltage source. The other ones have no source. So which mesh should be avoided? No mesh should be avoided. Deduce all the equations which permit to find the currents in the circuit. Now we start to make equations. We've done everything else. It's now just making equations. You just go to the nodes. Come on, this is so easy. At node A, what is going on? So we're going to have, we can say at node A, what is going on? The current coming in, I1, should be equal. You subtract the currents going out, minus I2 minus I3 is equal to 0. Then you're going to have node B. Who is going into node B? I2. Who is going out? I4 and I5. So what is it going to be? What is it going to be? You're going to say at node B, I2 minus I4 minus I5 is equal to 0. Should always be equal to 0. Then you're going to have node C. What happens at node C? The current coming into node C, we have I3. Another one, I4. Who is coming out? I6. I6 is coming out. So you're going to have I3, I4, and I6. You're going to say I3 plus I4 minus I6 is equal to 0. Then you are now going to have node D where you have your branch code. This is I1 because it's the same as this one. It's the same branch. So who's coming in? I6. Another one? I5. And what are they doing? They are adding to give you I1. So, but remember, we actually don't need it because it's the node at the border. It's the node where everything comes back together. So we don't do it. We don't do it. The node where everything comes together, we always ignore it. We call it the ground node. So we always ignore it. Now let's do the other ones now. We do the meshes. So we have these three. And what are they called? They're called KCL equations. Equations that are done at the nodes. Then now we're going to have our KVL equations. Let's put, what do we use to put our KVL? Our mesh. We said if the current is in the same direction as the mesh, then we are going to do what? We are going to make it negative, that thing, that resistor and whatever. Okay, so here, let's start with this source. So if we are going to go this way, when we get to this source, we hit low before we go to high. So we are increasing, so it's going to be positive. So it's going to be positive, so it'll be 15 volts. We don't have to put the units. Then now, it is going to go around like this. And now it is meeting I2. Where is I2 going? Down. Where are we going? We are also going this way, so we are going down. So it's going to be negative, so it's going to be minus V at that R2. Okay, we can call this our R2. Then here we have another one here, so we can call it our R3. And where is this current going down? Where are we going down? So it's going to be minus VR3. This is equal to 0. So it's going to be 15 minus. That V is going to be 15I2. So it's 15I2 minus. The other bit is going to be 15R3. Is equal to 0. You'd say 15 minus. There you go. This is going to be, 15I2. Then this other one is actually not 15, it's 200. So it's minus, this is going to be minus 200 R. It's 20. So it's minus 20 I. What I is moving in here? What I was it? Was it I4? So this is I4. So I4, this is equal to 0. And there's going to be equation number 4. Then for us to, for equation number 5, we say mesh 2. Which way are we going? We are going like this. So when we go like that, like we are going like this. How do we meet the R2 is going to be, it's going down, we are going up, so it's going to be what? Positive. So it's going to be, let's just do it right now. R2, so it's going to be 15I2. It's positive. Then here we have 11 and I3, but they are facing the same as us, so it's going to be minus 11I3. Then we have 14. No, it's I4, and it's by 5. And we are going against it, so it's going to be positive, plus 5I4. Is equal to 0. This becomes equation number 5. One more, which is equation number 6. That's mesh 3. Mesh number 3, what do we have? If we go like this, you can see we meet that branch current I4, which is opposite to us, so it's going to be positive. So it's going to be minus R3 I4. Then we have this, that R3 is 20, so it's like 20 I4. Then here it's going to be minus 5 I. This is supposed to be an I5. Oh my goodness. So for mesh 2, no, for mesh 1, there is no I4, it's actually an I5. That's why mesh 3 is going to be 20 I4 20 I5 minus 5 I4. Then we go down, moves I6 is going to be minus 21 I6 is equal to 0. There you have the third equation, and you are done. You have your 6 equations. Now we are going to have question 3 and question 4. I'm sure you can do question 3 and question 4. It's the same. You just come, there's a node here, there's another node here, then we are going to have the ground node here. So, of course, when we are dealing with the nodes, we're only going to deal with 2 because we don't deal with this ground if we are doing our KCL equations and stuff. Because here is going to be mesh number 1, mesh number 2, mesh number 3. Then we're going to have question 4, which is again nodal analysis for question 4. And as long as the nodal analysis, does it ever change? No, it can't change. Look for your nodes in question number 4. Look for the node. 1, 2 more nodes. Now, since you're going to have another thing here, so we should separate and have 2. So here, when we have done this now, we can be able to do more. So anyway, you're going to have these things. Then we are going to apply the things that they need us to do, and it should finish it off in no time. Question 3 and question 4. So you do this question, and it's for nodal analysis, okay? You just see us make the KCL equations in each node and whatever, that's it. I mean, anyone can put them. You can say this is your node A, this is your node B. You put the currents coming out. If you want to call this I1, then this I2, then here I3, whatever. You can put it. Then after this, we are going to have I4 and another one which comes, which you can call I5. So you'll be having the currents, and now you can start to add them and create it at whatever in the meshes. And you have your 6 equations. I know you can do that. If you have a question with anything which is remaining, then you should say it. Now for here, if you are doing it, you'll be saying for the next thing now, what you do is here. I mean, I'm sure you can be able to do this question number 3 in no time. That is why I'm counting on you guys. I'll tell you a secret about this question. We'll talk about it, don't worry. Here, this question. You can start to put, so here for node analysis, when you're actually doing it as a calculation now, will be, remember we have our branch, we have a branch here. We're going to have another branch here. Then we're going to have another branch here. Right. And I want to teach you something that is done here. When you're going to have a current source that is going to be in parallel with your resistor, like say this one, then we have another one which is like say this one. What you're just going to do before you continue is you're going to change those current sources to be voltage source. How? You just multiply the current by resistance. V is IR, current by resistance, then you get voltage, which uses the source. So in here you'd say, okay, this is going to be same. Then now what you're going to say, you'd say 47 times 3. If you say 47 times 3 in the calculator, you get 141, which is going to be like this. So what you'd have is, it would still be in series with the 47 ohm. It doesn't go anywhere. So it's like you'd say, okay, here we have another thing. Here we have this 7 amp with the part with this. So we would need to put them in series. So it would come like this, become good, then you see when you're having it, you'd say 7 times 9, you get 63. So it's 63 volts. It's now in series with 9 ohms. There we have. You'll be drawing something which you can work with. This is still 32 at the bottom here. So, yes. You have it like this, and this is going to be 25. There we have it. I mean, obviously, when it's like this, now anyone can work with it like this. This becomes very simple now. Okay? This becomes very simple. So what did we actually have? Remember the values that we had. Okay, so we're going to have your 141, you're going to have your 63. And if you look at the current source, it tells you that it was facing there. So that means this one, yes, it'll be like this, so that the current can go there. In here, it was facing up, so it should be. So now here it's going to be positive, negative. This is going to be positive, negative. So when we work with that, we can now resolve. Now we can resolve. These three are in series, so just add their resistance: 47, 9, and 32. Let's put this. If you're going to put, you'd say, okay, this is going to be 12 ohms, this is going to be 32 volts, this is going to be 25 ohms. Then for these ones which are in series, you add them to each other. And get one resistance, then you're going to add the two sources, knowing that this is positive, this is negative, and you're going to get also something. So that's how it works. You get values. So you actually end up having, should have one resistor, so yeah, that is what is going to happen. And we can finish this off whichever way we're gonna go. You can have this branch here. You can talk about this one. So anyway, if we start getting, now we are doing nodal analysis where we actually have values. Okay. Let's see here. All this is now just about application. Remember to add the so let's make let's go to, we can do our nodal analysis, and then from then on we can start to work on it. Like, so now you have point A, then you have point B. So in here, if we're doing, we do branch by branch. So in here, what do we have in here like this? Then You can put, so when you're doing the thing, you'd be saying, okay, you'd imagine that there's some voltage at the source here. It's here. We remove 32 because it's going to come like this and go down, which is going to positive, so it's going to be, you can say, and you can see it's positive, the negative. We are going top to bottom.
Okay, sorry, sorry. Wait. Let me mute. Give me a sec. Give me a sec. Can you hear me? Either way, you can finish this one. It's like if you finish, you're good. If this one comes, so what we you'd be saying. Remember, you are starting here, so always you want to end up at the. You should go to your nodes, right? So it's like you always want to end up at the ground node. So this is like the ground at our ground node. So that's where we are going. So let's see how we come from node to go to the ground node. And we'll be talking about all the branches, but we'll be dealing with them in terms of voltages, okay? So if I'm moving in this first branch, I'm going like this, right? What do I meet? I meet this 12 ohm resistor, so I'll say V12. Now, remember that I have branch currents, which I can say that for my branch currents, put your branch currents the way you want. Put your branch currents the way you want. So if you want, you can say in this branch current, I'm going to put a current I1. Okay, then you're going to have another branch current if you call I2, then I3. Now, when we are going to do our nodes, there's a simpler way to do this nodal analysis, and it is you go to every node and you imagine there's going to be a voltage there. Okay, this is one way to solve. So we're going to imagine that there's going to be a voltage here called VA. That's only for this last question that we're doing this. So I'm going to imagine it's a very very short because we have many sources. It's a very very short question. So I would say I have VA, right? And this is going to be, if I now want to come from this at A to go to my ground at B, what do I do? It's going to be VA. Then I'm moving like this. Do I meet another source? That's always what I want, what I need to. Okay? So do I meet, am I going to meet any source? Yes. And where is this source facing? It is facing upward because positive is up, so it's facing there. So it is subtracting, so it's going to be minus 32. It's VA, which is a voltage, minus this 32. Then we always divide by any resistors that are in that branch. If it's 1, it's 1. If it's 2, we put them in. So this is over 12. Then I'm going to say I take this second branch here going to the ground. It's going to be, so we say plus, it's going to be VA. Then do I have any source to subtract? No. Then I divide by the resistance in the 25. Plus, I now say in the third branch, what is it? VA. Do I meet any source? Yes. Where is it facing? Downwards, because it's positive is down. It's facing. So it's going to be actually an addition. So we say plus whatever the thing here was. What was it? When we changed it, remember you multiply. Okay, in here, what we're going to say 141, which is facing there. Then we subtract 63 because 63 is facing up. If I punch in the calculator, 141 minus 63, 88. I get 88. Which 78. Okay, I get 78. Then for the resistances, I say 47 plus 9 plus 32. 47 plus 9, that's 56 plus 32. That's 88. This is the 88 ohms. So now what I would say is, I would say VA plus 78 divided by the resistances, 88 is equal to 0. I'm going to have that. And if you want, you can start to add. So you combine this two. To add things, you put them over the same denominator. And for you to put over the same denominator, you just multiply the two, you get whatever denominator. Then you can now start to say, you put common denominator plus here, it will be VA plus 78 over 88 is equal to 0. You then find common denominator with this second one, because what you'll be just, and to find common denominator, you just multiply the two. And what you'll be now just trying to do is slow it down so that you can be able to find your VA. In here, you can easily find what your VA is going to be. And once you find your VA, you can start to find the branch currents, I1 and whatever, because this is going to be I1, this is going to be I2, this is going to be I3, the branch. And you can have your currents. Once you have these branch currents, you can now start to work with everything else. And what you can actually do is you can actually then go back then and put them, because you can actually then go back and put them at the and look for all the missing currents, slowly missing currents, and find out how you can work with them, these missing currents here. Let's talk about finding VA. We have to find VA. This is why it's so important for VA. You can find common denominators like 12 times 25. If you get 300, you'd now say 12 into this, you get 25 times this, it'll be 25 VA minus 25 times 32, then plus this is going to be 12 VA, because you'd say 25 into 300, you'd get 12 times VA, you'd say plus 12 VA, all that, and you'd add, and you'd be combining equal to 0. There's a lot of work to be done. You just combine until you find your VA. And like we said, you can now come to these branches and have branch 1, branch 2, branch 3, and whatever. And you can go back to also your original one where you had it like this in here. You had all these branches, if you want to call it I1, I2, I3, I4, whatever the names you want to call each branch, then start to find the VA and whatever. And VA is just IR, IR, IR. You'll be multiplying by RRRs, and you'll be getting it. And for you, what you should do is find I1 and I2. Then you can be going backwards and doing the rest, okay? Because I2 you find it in here, and you'd have the I3 in here as well, which you know that I3 was moving in here when you combined. So when you combine all these branches, that's when you must get an I3. When we had all these things that were combined and put into this one big series thing, when we combine them. So you can talk about that, okay? All adding to that. But whatever, we should find values, then we can start doing calculations if we can find this VA, and from VA we can now get the rest of the missing things. And I mean, whatever, this type of question is finished. Then you can do the one for network theorems where it's Thevenin. And you have Thevenin, and then you have for whatever other question that you're going to get. But let me say this, which is something very important for you. If they talk about power generated and then power dissipated, let's talk power generated is going to be VI. power dissipated is going to be I squared R. And you're going to get the total power dissipated, you get I squared R for all the resistors. Then you add those I squared R's, you get the power dissipated. For power generated is P is equal to VI. And you only have to get for P is equal to VI when you're dealing with this, okay, where we're going to say P is going to be VI, then what you must know is that you are not going to do for all the different types of things. Okay, you're not going to do for all the different types. But what you're going to do is when you're dealing for VI, remember you're going to have yes, to get the power dissipate, you'd need to know all the branch currents for you to get all that thing. Then, if you now want to find the power that was developed, you go to the most important things, which is like if you're looking at your source, okay, you'd be looking at your source and you'd say, okay, you'd need in the very first branch in here. So this branch is definitely very important for us for the power that is generated because there is a source. You look for all branches where you have your source and you're going to be saying just VI, VI, VI. All the branches that are going to have some form of a source. If there is no source, then we don't talk about it. So all the branches that have sources, that is where we're going to be doing. And you'll be just saying VI, the V, and then by the I in that branch. And it will give you the power that is developed, power developed, power developed. Power generated is just in each of the branches. Don't forget it. Then you'll be comparing to see if it's going to be the same. Okay. You'd meet these questions in the exam. These are the very same questions that come. This question we did, you can track back and you see us do this question. We've already done it, and you'd put your things, the missing things, and whatever you can be doing. Maybe the type of question I want you is saying, compare power dissipated and power developed. This is the type of question I would need you to know. Now, let me give you a tip of how to do this question. Power developed and power dissipated. You should have, this is going to be my I1. When you are now doing this question for power dissipated, throw away everything you have done up to this point. Up to this point, you know you are doing your I1, your I2, and whatever with your notes. But for here now, what you're going to do is you're going to need to be smart. And when you're going to need to be smart, you're going to call this I1, then you're going to call this I2, then you're going to call this I3. The rest we start from there. We're going to be building from there. Then we would say, what about this branch? What is it going to be? Well, we are going to have what? To get to this branch, it's just going to be I1 minus I2 for here. So it's going to be I1 coming minus that one of, so this is going to be I1 minus I2. Then here you have I3 already. So it's just about pop there. So you need to be able to find these things. You have your I1, which is going to be have your I2 here. This is going to be I1 minus I2, which I1 minus I2 comes to meet in here, and then we're going to have one that comes out. Then we're going to have another one that comes out. So to come in here, you know that this is I2, and I3 is being subtracted. So this branch is going to be I2 minus I3. Then in here, it's I1 minus I2 meeting I3. So it's going to be I1 minus I2 minus I3. No, in here you'd add your I3 because it's also coming to join in here. This is equal to 0. So once you have these branch currents,
This is now nice and easy and they're small like this. That's going to be very important because you can now put your meshes, your 1, 2, 3, or whatever. And for this one, we don't need any matrices. Because for us to then get these powers, which is going to be the power dissipated and the power developed, everything much it becomes much easier for you to solve. For this, how much power was dissipated, and all these other questions, which then ask you to say, please tell us how much power that was dissipated in whatever. You can't use it in that other state because they like to show you with matrices. Hmm? Remember that all these things, it's just a walk in the park. You have put your eyes. You have I1, I2, and I3. I3 was in this branch, if I can remember. In here, that is where we have. I2 is in here, and I1 is in here. These are the only three branches. Here you only need to have, so if you have this, you have all you need. Okay, if you have this, you have all you need, man. All you need is going to be here. If you have, remember, the only three currents you're going to need is your I1, your I2, and your I3. Don't forget. The rest is going to make it very easy. So once you have them, you can be able to find whoever is missing. Once you have these, your I1, your I2, and I3, you can be able to remember. For power dissipated, it's just going to be I squared R, so you're going to need to find all those I's. Then for power developed, you'll be adding VI's, VI's, VI's. That's what you do for power developed. It's completely different from power dissipated. And you can't have it in those big equations. But once you have it in this state, you can now come and use your nodes and start to apply nodal analysis, then mesh analysis, and everything is gonna be easy. Try to do it and see. It's gonna you now have much less work to find whatever is gonna be missing. So it's gonna be very important. Use that idea. Don't create 6 currents. That's crazy. Don't do that. You're going to have those three, only those three, where you have I1, I2, I3. Don't forget that I have told you. Don't forget that I've told you. And we can now apply our nodal analysis and our mesh analysis. Then the rest of the work becomes much easier. When you have these type of questions. I mean, when you have these type of questions, make sure you're gonna be fine. If you have them. I mean, yeah. For section B, remember how you're going to answer. Section A is kind of like a walk in the park. These are just questions that sometimes repeat themselves, small theoretical questions where you move piece by piece by piece, and yeah, it solves itself. Here you're going to have current, find the power developed, P is equal to VI. So here they said power developed by the resistor. So P is equal to VI.
where we know this is our I, this is our V is I, V is IR. So you can, for here, you would just say, here they said, find the power developed, okay? Then they're also saying, find the energy dissipated. So let's start by power. So power developed, you can, if you can't have VY, you can also say I squared R. Then for energy is just going to be power times here, power times time, which is going to be the whatever answer you get for power times 5 minutes, but you're going to say 5 minutes times 60 seconds. Then you're going to get an answer. Convert the following circuits. If you're forgetting converting to get Norton equivalent, this is easy. To do these conversions, you must just know that R Thevenin is equal to R Norton. So it's like crazy, man. To find the Norton, for Norton we need IN. So R Norton, we already know that the R Norton is going to be equal to 5.0 ohms. Then to get I Norton is like just saying V over V is equal to IR, or I is equal to V over R. So here it will be just V Thevenin over R Norton, which is going to be V Thevenin over R Thevenin, which is going to be it be saying 4 volts over 5.0. Then you're going to find the I naught. Then once you have it like that, you can just now make your once you have it like this, oh, it's gonna be easy because there's going to be your I Norton and your R Norton. They'll be in parallel. And here, calculate the supply current, and they give it like this. Well, what you can see is that these things are in parallel, so there's going to be 110 volts here and 110 volts here. And we know that I is equal to V over R. They say the supply current, so you'd know how to do it. Okay, V over R, 110 over this, 110 over this, and then we can. These are very small questions that come in section A. Yet it is now saying, can you please find, determine I1 and I2? I1, I2, okay. This is I2 and there's I1. So anyway, we know I3. How did we get it from current divider? Here. So what we would have said is I3 is going to be the other R, R2 over R2 plus R3 by I1 is the one that is coming into here and sharing. So the one we need is I1. We just make it the subject. I3 multiplying R2 plus R3 divided by R2 is equal to. you can easily find I1, which you then know that I1 is equal to I2 plus I3, which you can find the missing. Here you can do that using what I've just shown you. I think you'll be fine. Because if you want to get I2 now, you'd make it the subject I1 minus I3 is equal to I2 and all that. Anyway, 1 mark questions are like a joke. Here, the two capacitors are connected in series. Calculate the PD across each capacitor, the charge on each capacitor. So if they are connected in series, we can talk about this supply, and it is going to be shared between these two. So you can still call it voltage divider. They said find the PD across each. So if you want V at 6, this is going to be 6 over 10 plus 6 by 200 volts. Then you can find how much. Then obviously for the 10 ohm thing is just 200 minus this one, and then you'll be fine. The charge on each capacitor, we know that Q is equal to CV, so you'll be just multiplying CV, and then you can get. Anyway, blah 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 blah. This question, calculate the flux. Flux is this one. It is equal to BA, or we can say BA cos theta. Yeah, that's 90, so we can just say theta is equal to BA, and we can find it. In this question, a rectangular coil is so that it can be rotated at the about the midpoints of the hundreds. Is it right angle to whatever? This is going to be my B. And then now I need A, which is going to be area. Okay, so here you've been told that in this case, we have our B, we have found it. A is now just the area. It's a rectangle, and we have been told this, you can get A. you can put, when it's 90 degrees, I say just put BA as your thing. Well, here is whatever say whatever they're saying. The closure T go to 0 into position 1. They said determine the mathematical expression for the variation of current in the inductor following the closure of the switch. So anyway, this is about inductors, which we don't really want to know, but you should just want to know. They say the variation of the current, so they just want to know what is the equation. Okay, at t equal to 0, they want to see if you know for charging and discharging when you are dealing with an inductor. For charging, what is it going to be? They want an expression for what? Current. So you're going to say IT is equal to V over RL multiplying 1 minus E This is what you'd actually have. Then given 8, whatever. Angular frequency is this one. This is omega t. So angular frequency, you have it as your 60 theta degrees. Then period is 1 over 2 pi. Well, even if you look at all these other things, the frequency of the applied, the resistance, when you have a source like this, let me see how many. Oh, it's just 2 more. A capacitor, blah, blah, blah. Calculate the frequency, So a capacitor is 8 microfarads, takes a current of this, and this is the capacitance, this is the current. Applied, this is the voltage. The resistance to be connected in series with the capacitor, reduce the current, whatever, same frequency. These are just 1 mark questions, honestly, and this is 2 marks. You should be able to do let's see here. Like, okay, so here we can see our resistor in nice series with this. Then you have this. Then they can ask you to say what is the they can ask you to say what is the frequency of the applied voltage. This is a very, very common question. So you guys should get used to this question if you are ever asked, so that you can be able to quickly solve it. Okay? Because here